you are looking this problem. So just we have to compare the saturation temperature. So the actual temperature is less than the saturation temperature. The state is compressed liquid. So we have to take these specific velocity, specific volume at a specific volume of a fluid at 25 degrees Celsius. Just if you go to your property tables, then you can't look at this 200 kilopascal. Just you have to go with the 25 degrees Celsius. The corresponding, yes, the approximate value will be around 0.001003 something. So you can that this property is for half reservoirs only. So we can calculate the volume, that is specific volume is equal to mass by volume. So we can derive this equation, volume is equal to mass into specific volume. So we know the mass, then we found out the specific volume. If you multiply these two, we can get the volume of the half reservoir. So the volume of the half reservoir is 0.005 meter cube. Then the initial volume for the entire tank can be, so because we partition into two half, right, two equal parts. So the volume for the whole tank will be 2 into the volume of the partition. So we have the volume reservoir as 2 into 0.005. So that is 0.01 meter cube. So we found the volume of reservoir. Then we can move to the state 2. So they gave the state 2 temperature is again 25 degrees Celsius. Then we know the V2, right? So we know the volume of the second state. So this 0.01 is your volume of the reservoir. So if you divide that volume by mass, we can get the specific volume of the reservoir, that is for state 2. So if you found that specific volume, so we can get 0.002 meter cube per kg. So as you know already, so we have to compare this specific volume in your property tables. So we can take the corresponding value of temperature 25 degrees Celsius. Yes. So we can take the just you can go to your temperature table. Yes, in table A4 there is saturated water temperature table, so you can get the temperature. Yes, 25 degrees Celsius corresponding values can be taken. Then we have to look at this specific. We have to compare these specific volumes. So this our calculated specific volume, that is 0.002. So we have our specific volume for gas, for fluids, and we have specific volume for gas taken from the tables. So we have to compare these three values. So 0.002 is obviously in between these two values, I think. Yes, in between these two values. So we have saturated mixture, that is second condition. So we can directly take P2 is equal to P saturation. That is, we can take the pressure from the same table. So if you look at this table, we can take this pressure. That is 3.1698 kilopascal. It's our state 2 pressure. Yes, state 2 pressure. Then we can apply the heat transfer for this process with the use of energy equation. Q net minus W net is equal to M into delta U plus delta KE plus delta PE. So for the constant volume, we can neglect these three. Then we can have Q net is equal to M into delta U. Then this delta U can be written as U2 minus U1. Then, so how can we calculate the U1? So we know we can take the U1 value for the same values corresponding to the V1. So if you take that U1 value will be, yes, if you take the U1 value will be 104.88. Yes, you can check in your property tables. Then we need to found X to get U2. To get U2, we need to found, because this is a saturation mixture. So only for saturation mixture we need to found X. So at state 1, the state is liquid. So we need to but at state 2, the state is saturation mixture. So you know how to calculate X. We can use the Y formula. That is Y is equal to YF plus X into YFG. So for at state 2, we can calculate with the corresponding value of this. So at pressure 3.169, temperature 25 degrees Celsius, we can take the corresponding value of VF and VFG in your property tables. Then we can calculate the X2 values. So if you calculate the X2 values, then we can use that for your U2 calculations. So that U2 can be UF plus X into UG. So you can get the UF value and UG value alone. So if you want to calculate U2 value, you need to count this X. So we calculated X as 2.3 into 10 to the power minus 5. Then we can take the UF value from your table. Then we can take UG value from your table. Then if you put the values in the formula, we can get the corresponding value of U2. That is your internal energy at state 2. Then yes, so we have U1. Then we have heat transfer. Then we can directly apply this to get the U. That is Q net heat transfer. So if you calculate, the value will be in positive, so 0.25 kilojoule. So we have to, the heat is added to the system, right? So heat is added to the system. If negative, heat is removing from the system. So we can get positive signs indicate heat transfer into the system, right? Into the system. If out of the system means there will be some negative. So this is the application of your energy equation for constant volume process. So I think already gave these problems in your assignment, but none of you tried to solve this problem. Just try to solve these problems also and try to upload that. So already I gave a marks to only one person. So I think Iman Chandra or something. So he's not uploaded this assignment. Others are uploaded. So just try these problems also. So in your assignment there was exercise 4. So in that exercise 4, these problems will be there. Just try to solve the problem. So this problem 1 will be same as this problem what we discussed in this class. This example 3.3, but the state is here we use water, but in this problem at your supplementary problem, first problem, we use carbon monoxide. We have to look at the carbon monoxide property table. Then try to solve. So these problems will be same. That is for constant volume process with the application of energy equation. So we can try to solve. Just try and upload your answers in your Teams assignment file within next week. Right. Right. We can move forward. So also there was 5 questions you have to complete. Right. So the next chapter is closed system, first law of cycle. So this is for cycle. Right. Also we have closed system, but for a cyclic process. Yes, some thermodynamic cycle composes of a processes in which the working fluid undergoes a series of state changes such that the final and the initial states are identical. So in the previous classes, we looked at only one process. But if 2-3 processes get combined and the initial stage and final stage are in same property, then we can call that process as a cyclic process. So here we are going to look at what are the cyclic process and the applications of that. So for such system, the change in internal energy of the working fluid is 0. So we can get the change in internal energy, that is delta U in the system is 0 because the initial state and the final state will be same. Then we can have the first law for a closed system of a thermodynamic cycle becomes Q net, that is change in heat transfer net system minus W net. Net in the sense all the processes. So there will be 2-3 processes. So first process heat transfer plus second process heat transfer plus third process heat transfer can be added to get our Q net. So total of all the Q, then total of all the W equal to total of all the internal energy. So we know this delta U for a cyclic process is 0. Then we can have the equation as Q net will be equal to W net. So if you add heat to the system, then that heat energy will be directly transferred into your work. So that is a definition of this equation. Q net will be directly equal to your W net. So already we discussed this. So this is the PV diagram of all the processes. So this one, line 1 will give you constant volume process. This line 2 will give you constant pressure process. Then this line 3 will give you isothermal process. Then this is for what to say? This is for polytropic process. Then this is for isentropic process. So we can compare this in the next slide. So you will get the first line isochoric process. Then we know how the isochoric process look like. So there is constant volume. So V1 will be equal to V2. Then we know the ideal gas equation, that is P1 by T1 is equal to P2 by T2. So these were already we discussed and we derived. So just go to a quick look on this table. Just you can compare the graph with this table. Right. So the second line isobaric constant pressure. So P1 equal to P2. Then we can have the equation as V1 by T1 equal to V2 by T2. Then the third graph will show you isothermal process, that is constant temperature. So T1 equal to T2. Then we have the ideal gas equation as P1 E1 equal to P2 V2. So here we introduce a polytropic. So polytropic in the sense PV power N. Yes. So if you take this law of ideal gas equation, so we can take PV, the ideal gas equation as PV is equal to MRT, but we can change the equation as PV power N equal to constant. So this law can be applied for all the processes. This law can be applied for all the processes. We can call this equation for polytropic process, right? So if we can compare the n values here, we can compare the n values here. So if n value is infinitive, so that is for constant volume process. So we have infinite volume, so that with, so we can have p is equal to constant. If the n value is 0, can so n value for isobaric process is 0, then n value for isothermal process is 1. So if n value is given, so we can take the n values and we can apply in this formula. Then we know what is isentropic process. So in this, the isentropic value is mu, right? So we know the formula. So in isentropic process, the constant entropy, so Sn will be equal to S2. Then we can have the equation as P1 by P1 by P2 equal to V2 by V1 power n. Then in the terms of temperature, T1 by T2 power n by n minus 1. So this is for polytropic process. So if n is given, we can directly take this for polytropic process. If gamma is given, just we can apply the as gamma, right? So if for isentropic process, the energy equation will be P1 by P2 equal to V2 by V1 power gamma, right? So for temperature, T1 by T2 power gamma by gamma minus 1. So this is the of our thermodynamic processes. Then also we can have the for the all the processes. So already we derived this work W. So for isobaric process, W will be equal to 0. For isobaric process, W will be P into delta V. And for isothermal process, W is equal to P into V natural logarithm of V2 by V1. Then for polytropic process, we can have W as P2 V2 minus P1 V1. That is yes, P2 V2 minus P1 V1 by 1 minus n. So if isentropic, you can take P2 V2 minus P1 V1 by 1 minus gamma. So you have to remember these formulas. So we know how to derive these equations. Then we can directly go to the problems. Of 10.5 kilojoule from an initial volume then the second process is isothermal compression. Then the third process is isochoric heat transfer to its original heat transfer. Yes, we can tell this process is a cyclic process because initial state and final state are equal. That is V1 and V1 values are equal. So we can we can draw the PV. We need to calculate the volume of all the process. Also, the second question, the isothermal work. So we need to calculate the work of all the process for the isothermal process alone. Then we need to calculate the net work. That is, if you calculate all the work, we can add all the work together to get a net work. Then fourth question, heat transfer during isobaric expansion. So we need to get a heat transfer, that is Q. So for this, we need to apply the energy equation. Right. So we can move to solve the problem. So first process 1 to 2 will give you isobaric process. So we know for isobaric process, that is W is equal to change in P into delta V. So V1 value and V2 value are given and P value also given. So we can calculate the W12, that is for process 1 and 2 for work value. Right. So V2 is not given. So they gave V1 value alone. Right. So they gave V1 value as a 0.028. So then we have the value for W. So if you also we have the value for P. So if you substitute, we can found the V2 value. This volume at state 2. So that will be 0.103 meter cube. So you can compare. This is the first process. So first process is constant pressure process, that is isobaric process. So if constant pressure process, in this constant pressure process, there is a reduction in, sorry, this process, constant isobaric process, constant process. So there is an increase in volume, right? So initial volume is 0.028 meter cube. Yes, final volume is 0.103 meter cube. So there was increase in volume. Right, there was right. So we can go to the next process, that is isothermal process. You know the equations, PV is equal to constant. We can take so isothermal process will be like this. So we can have the isothermal curve, isotherm. Right. So if you calculate, so we have V2 value, then we have P1 value, and also we have P3 value. Right. We have P2, we have V2, and we have P3. We need to calculate. Sorry, we have, yes. So yes, you can take these two states, that is state 2 and state 3. So we have V2 is equal to P3, V3. So at state 2, we know what is pressure, then what is volume. At state 3, we know what is volume. We know what is volume, but we don't know what is the pressure. So we can calculate that by the equation. So if you put the knowns value in the equation, we can get the unknowns value, that is 515 kilopascal. So here pressure will be 515 kilopascal. So at this point, so pressure is 140 kilopascal. So it was, yes, maximum. Yes, so 515. Yes. Also, we can calculate the work done, W, for the process 2 to 3. So we know the equation, W is equal to PV ln V2 by yes, V2 by V1. So here we have a 2 to 3 process. So we get just write the equation accordingly. Right. So the final state by initial state. So we can get the W also. So W value will be in minus 18.78 kilojoule. So here it's a thermal process. So work done on the system is there. Right, we can move to the next process, that is from 3 to 1. 3 to 1 will give you the constant volume process, that is isochoric process. So you know, in isochoric process there is no W, so we no need to found any other properties of the state. So we know the uh, P1 V1, and we know P2 V2, and we know P3 V3. Then we need to get the W values net. Yes, the question is, we have to the maximum value, calculate the maximum volume in the cycle. So we can compare the volumes, and we can yes, here we have V1 and V2. So this V2 is maximum, right? This V2 0.103 meter cube is maximum. So we answer the first question, and we can isothermal work. So isothermal work in the sense isothermal process, W223 will be minus 18.78 kilojoule. Then the next question is net work. So we can add the works together. So W12 plus W23 plus W31. So you know W31 is 0. If you add these two, so we can get the W net. So 10.5 plus minus 18.78 will give you W net. Yes. Is there any questions? Also, we could find the heat transfer during isobaric process. Yes, there is isobaric process. So we can apply the energy equation. Yeah. So we know this is a so for that we need to again look at energy equation. So we can find the fourth question in the next class, that is heat transfer during isobaric expansion, will be discussed in the next class. So before that we can look at the next problem. The fluid at 4.1 bar is expanded reversibly according to law of PV is equal to constant. You know, PV is equal to constant is for isothermal process. To a pressure of 1.15 bar until it has a specific volume of 0.12 meter cube per kg. It is then cooled reversibly at a constant pressure. Then is cooled at a constant volume until the pressure is 0.62 bar, and is then allowed to compress reversibly according to the law PV power gamma, PV power n is equal to constant. So this is the polytropic process. Back to its original condition, the work done in the constant pressure is 0.525 kilojoule, and the mass of the fluid pressure is 0.22 kg. Calculate the value of n in the fourth process, the net work of the cycle, and the HC PV. So here we have four processes. So just try to get the what are the process. So first process, if you look at this graph PV diagram, we can get the first process is isothermal process. Then second process is isochoric process. Then we can isobaric process, then isochoric process, then polytropic process. So there was four processes happened. So we can try to get the all the values properties of all the states, right? So in first process, that is isothermal process, we know the equation PV is equal to constant. So we can have P1 V1 is equal to P2 V2. So P1 value and P2 value and V2 value is also given. Yes, I think. So V2 value is not given, but a specific volume is given and mass is given. Specific volume 0.22 bar. Yes. Specific volume and the mass is given. We can get the volume V1. So that can be used in the then if you have the V1 value, we can calculate the W value by the use of this formula. The W for isothermal process is V1 ln power ln into V2 by V1. So we can calculate the W as 3.895. Just try to use your calculators. Just cross check the values. Then only we can get the PN. Just practice your calculators. So that will be easy for your examinations. So that will save your time in your examination. So just try to cross check the calculations here. If you calculate, the W value will be 3.8 kilojoule. Then we can move to the next process, isobaric process. Here, so isobaric process, we know P1 equal to P2 equal to P3, and we know V2 also. We don't know V2. Yes, we have to find V3. Yes, let me take. So the pressure is constant, so we know the pressure value. Then we have the volumes. Then we can W value is given. Then we can find the volume of 3. We 0.03097 meter. Right. So we know next process is constant volume process. So V3 will be equal to V4. We need to find P4. Yes, we can try to solve. Yes. But we don't have any other. We know for isophoric process W is equal to 0. So W34 will be equal to 0. Then for process 1 to 4, then 4 to 1, it's polytropic process. Then we can have the equation as a P. Yes, P final by P initial equal to B initial by B final power N. So we don't know the values of N. So we know the values of P4, P1, V1, V4. So the known values were substituted in this equation to get your N. So the N value will be 1.3182. So just write this natural integration. If you get N value as 1.31, we can use this N for the calculation of W. So So W can be calculated by the use of this formula. P1 V1 is equal to P final V final divided by 1 minus N. So we know the value of 1, then N, we know the value of P1 V1, we know the value for P4 V4. Then if you substitute, we can get the W. Then the W value will be minus 3.5124 kg. So we need to calculate the net work done. So net work done will be W12 plus W2 to 3 plus W3 to 4 plus W4 to 1. So we can add the work all together to get W net. So if you calculate, the W net will be 0.9076 kilojoule. Just cross check the values. The thing is, you have to use the W formula and the equation, ideal gas equation for the consumption processes. Yes. So also these problems in your assignment, just try to solve these questions also. So these also will be same as previous. Yes, the thing is you have to know the W equation and the gas equation, ideal gas equation for the concerned process. Then you have to be able to identify what is the process. So we have a lot of process, so isothermal, isobaric, isentropic. So we have to be able to found the process based on the data given. Then try to these problems and try to submit before next week. Then this is the important chapter, first law of thermodynamics for mass and energy analysis of controlled volume process. You know controlled volume process in the sense that is open system. For an open system, we can transfer mass and we can transfer energy, right? So that can be called as a controlled volume system. So we can control the volume of the system. Yes. So before that, we need to understand conservation of mass. What is conservation of mass? Conservation of mass is one of the most fundamental principle in nature. So we already see we normally see in our nature there is conservation of mass. So we are all familiar with this principle, and it is not difficult to understand it. The conservation of mass in the sense, so if mass is transferred from one place, another mass will try to occupy that space. So that is conservation of mass. But for a closed system, the conservation of mass principle is implicitly used since the mass of the systems remain constant during the process. So we can able to tell for a closed system the mass is this much. So if this mass is transferred to any other place, then we need to fill this much amount of mass again. So let's compare the closed system. We can transfer the mass of unknown values. However, for a control volume, mass can cross the boundaries. So the amount of mass entering Anusha is there. Karthik.
சார்
கேக்குதாமா?
கேக்குது சார்.
எஸ் சார்.
ஓகே ஓகே. Right. So constant volume, the control volume system can be transfer the mass of the system. So the mass and volume flow rates can be discussed in this slide. The mass flow rate is mass flow through a cross-sectional area per unit time is called a mass flow rate. So repeat, mass flow rate is mass flow through a cross-sectional area per unit time. That is can be denoted as m dot. M dot indicates mass flow rate. Yes, the dot over the mass symbols indicates a time rate of change. It is expressed as m dot mass flow rate equal to integration of rho v into change in this dA. So area, volume, then we know the rho density. So if you know this, we can calculate the mass flow rate. Just take down the formula. M is equal to integration of rho v dA. That is mass flow through a cross-sectional area per unit time. Right. So if the fluid density and velocity are constant over the flow cross-sectional area, the mass flow rate can be. So we can have the again m dot as rho into a into v. Then this we know what is the value for v. Then we know v specific volume equal to volume by mass. Clear? So we can write, then we know density equal to mass by volume. Then we know density is equal to mass by volume. The density value, that is mass by volume, we can get v by the density is equal to mass by volume. Yeah. Yes. So we can have the equation as mass by volume. So this can you delay this? Yes. So we know for volume we can put these values. So v will be equal to, volume will be equal to mass into specific volume. So we can substitute this in this. So we can be it is rho can be equal to here mass divided by mass into specific volume. Just wait a minute, ma'am. Senior. Sir, when you put class back. If you substitute, then the rho value can be replaced as we can cancel this m. Then we can have 1 by. So that was replaced here. We can have m dot as a by v by V. So this rho can be replaced as 1 by specific volume small v. Yes. Yes. This is the derivation. So V small v is equal to 1 by rho. Then you know what is small v? V is called specific volume. Then the principle of conservation of mass can be written as mass flow rate in minus mass flow rate out equal to mass flow rate of constant volume. The conservation of mass principle for a control volume can be expressed in. So if you want to calculate the control volume, so mass will be in, some mass will be out. So we have to calculate the net mass transfer of in and net mass transfer of out. Then assume the process is steady state, steady flow process. So these are your fluid dynamics portion. So just try to found what is steady state and steady flow process. So steady flow in the sense there is no change in the flow. So we can get a frequent flow in the liquid or any gases. So steady flow in the sense that there is no distractions, right? The conservation of mass principle can be written as, so for a constant steady state steady flow process, we don't have this control volume. So control volume can have mass in and mass out, but in steady flow process we can neglect the mass in and mass out. We can assume the mass in will be equal to mass out, right? So that is called a steady state steady flow equation. So in steady state steady flow equation, the amount of mass entered will be equal to the amount of mass exit, right? The net flow rate of mass in will be equal to net flow rate of mass out. So the unit will be in kg per second. Just try to remember. So steady flow process, the m dot in will be equal to m dot out. So this is the control volume process. This is a control volume system. So control volume in the sense we can transfer mass, we can in mass to the system, and the amount of mass can be out from the system. Then we know the property of the system at inlet, that is we have the property volume, we have the property pressure, we have the property mass, and this is also as the fluid upstream pushes mass across the control volume. So this is a control volume. So if you push the piston by some force, the work done on the unit of mass can be expressed as W flow will be equal to force into change in length. So we can change this length by applying. So we can have W is equal to force into displacement. And in this control volume process, control volume process, we can write the flow W equation as F into change in length. So we can have F. So this amount of area, so area here, cross-sectional area will be equal to this. So can you multiply and divide by area, you can have the FDL equation as F into dV. P into dV, because you know this change in area into change in length will be your volume, change in volume, and you know force by area will be your pressure, right? Pressure is equal to force by area, and the change in volume will be equal to change in length into area. So we can write the equation as P into dV, and also we can expand this equation as P into small v into change in mass. So this, V is equal to, this capital V is equal to mass into specific volume. Right. We can introduce the terms because the mass here is changing, so we can have the change in mass. I think some of you gets problem. Saujanya, Manish. Okay. Right. Yes, some of you messaged me. I will rejoin again due to network issues. So there is not a problem. Just try to try to follow the classes. So if you missed some any of the portion, yes, you can download your videos. Then you can get understand. Right. Where are we? So W can be written as P into small v into change in mass. So yes, the organ flow will be this small w, right? Specific work done can be written as work done divided by mass, like this, like this. So small w will be equal to capital W divided by mass. So here we have a change in work and change in mass. So we can write this equation as delta W flow equal to delta capital W flow divided by delta M. So this will be equal to, so we can bring this here. We can have capital W by small m will be equal to the remaining portion P into V. The thing is, the specific work done will be equal to capital P into small v. So pressure into specific volume for a control volume process, and the total energy of flowing fluid can be calculated by the use of energy equation again. The total energy carried out by a unit mass as it crosses the control surface is the sum of the internal energy plus flow work plus potential energy plus kinetic energy, like our energy equation. So energy of the steady state steady flow will be equal to, yes, that is U, that is a change sum of internal energy, change in internal energy. Sorry, here we have in and we have out. So we have to write separately. So we have the whole equation is energy equation is E is equal to U plus PV, or we can say this as H. This as H. So U is internal energy, PV is flow work that we know, we calculated now. Then we know potential energy, then we know kinetic energy of mv square, then mgh will be equal to, so we can write the same as this. So we can write U plus PV as H, then we can have this equation H plus potential energy. So here m is constant, so we can take this side. Right. The first law for a control volume can be written as Q net, it's the net flow rate, minus outflow rate net will be equal to summation of out, that so we have in and out, right? So we have in and out. There is out will be second, then in will be first. So we can have m out into h plus kinetic energy plus potential energy minus for inlet, so outlet, minus m in into h in plus kinetic energy in plus potential energy in. Also, we can write this equation for steady state, steady flow, conservation of mass, and first law of thermodynamics can be expressed in the following forms as Q net minus W net is equal to H2 minus H1, that is plus V2 minus V1 by 2000, because the unit in kilojoule. Right. Then we have the change in potential energy. Then if you want to write in so capital letters, so we have to multiply with m. So m into delta small q will give you capital Q. So Q net minus W net will be m into this term. So we can have the general m constant. So we can multiply m with the both side. Then we can have this equation. So m into Q net will be capital Q. And m into small w will be capital W. Then we can have the equation as m into the same in kilojoule. Right. Also, we can have the the flow rate in the form of flow rate. So Q net dot minus W net dot will be equal to m dot, that is flow rate, mass flow rate, into H2, same change in entropy, change in kinetic energy, change in potential energy. The thing is, for a steady state, steady flow system, we can have this equation. Okay. So these are some applications of steady flow energy equation. So nozzle we already discussed in the introduction class. We know what is diffuser, what is turbine, what is compressor, what is mixing chamber, what is heat exchanger. So these are the that we use the steady flow energy equation. So if you take this nozzle, there will be flow and there will be a steady flow, and we can use the steady flow energy equation. Right. So in turbine flow, there will be flow, mass in, there will be mass out. So we can have this steady flow energy equation. Then diffuser also, there will be in and out. So we can look at what are these again. So then how can we apply this steady flow energy equation for this engineering devices in the upcoming slides. So we can take nozzle and diffuser. Can you able to imagine what is nozzle? The nozzle is a device that increases the velocity fluid at the expense of pressure. V1, you know what is V1? So this is inlet, this is outlet. So assume a nozzle. So just assume our tell me any application, any nozzle available? Nozzle. Right. Just assume this one. So nozzle will give you increased velocity. The velocity of the fluid can be increased with the use of nozzles. The diffuser is opposite to the nozzle, so the velocity gets decreased. The velocity gets decreased if the fluid is passed through diffuser. So diffuser is the device that increases the pressure of the fluid by flowing it down. So velocity will decrease, but pressure will get increased. The pressure will get increased, but in the case of nozzle, the pressure will decrease. Right. So we look at. So commonly utilized in jet engines. So you can look at these nozzles in jet engines, rockets, spacecrafts, and even garden hose. Yes. So just you can take this simple example of nozzle. Just in garden hose, you can imagine this nozzle. So the velocity of the water will be less in the flow, but by coming through nozzle, the velocity gets increased. Because of that only we can have the fast water, right? So just assume. So these are the applications of nozzles and diffuser, where we use steady flow energy equation. The flow will be in steady flow, steady state. Then, so for this nozzle and diffuser, the Q, there is no heat transfer, so we can neglect the Q. And also there is no work done. W will be there for a nozzle and diffuser. There is no work done because just the flow will be there. W will be 0, and there is no potential energy, so there is no elevation. But there is V. So you know, half mv square is related to kinetic energy. So there will be kinetic energy. Right. So in nozzle and diffuser, we have only kinetic energy. Right. So steady state, steady flow energy equation can be written as for nozzle and diffuser below. So Q in net transfer in minus net W in plus same. This is energy equation. This is in, then this is out. Right. So we can neglect these. Yes, so there is no entropy, there is no potential energy, there is no W, and there is no Q. So we can strike out this. Then we have only mass flow rate in into, sorry, we have H, because U into PV, right? So H is equal to U plus PV. So we have P, pressure here. So P into specific volume. So we can have this for the nozzles and diffuser. So the thing is, we have the energy equation as, so for we can also neglect this M in will be equal to M out for a steady flow. So we can have the final equation as H1 plus kinetic energy, that is V1 squared by 2 of V1 square will be equal to H2 plus of V2 square. Just remember this formula, then we can solve this problem by the application of that formula. Just assume, just read the problem. A steam at 0.4 megapascal and 300 degrees Celsius enter an adiabatic nozzle with a low velocity and leaves at 0.2 megapascal with a quality of 90%. Find the exit velocity. They gave P1. Yes, they gave P1 Also they gave P2. Also they gave V1, and 90% quality means X2. Fine line. Yes. Also they stated with a low velocity. So we can have V1 as 0. So if you apply the energy equation, so we can have H1 plus of V1 square equal to H2 plus of V2 square as, so we can, there is no velocity given, so we can neglect these velocities. Sorry, V1 is 0 because we neglect this one. Then we have to found these properties. H1 we need to be found, H2 we need to be found. So just we can follow the previous problems. Yes, we have P1 and we have T1. Yes, if you look at this, if you compare this in your property table, T1, that is temperature, will be greater than your saturation temperature. Just take for pressure table. Take the pressure table. It's wait a minute. I will open and show you. Yes, temperature table. Then we have pressure table. Then we have to look at 0.4. It's in kilopascal, so we have to look at 0.4 inductance. One saturation temperature is 143, but our actual temperature is 300 degrees Celsius. So the temperature is greater than the saturation temperature. We have to look at the superheated table. So the state is superheated. So we have to look at the superheated table to get the H1 value. So I will show you. You can go to the superheated table. A6 and pressure 0.4 megapascal. 0.4 megapascal. Yes. Yes. So we have to look at corresponding saturation temperature 400 degrees Celsius. Sorry, 300 degrees Celsius. If you took 300 degrees Celsius, we can take here H value as the third one. H value as 3067. 3067 kilojoule per kg can be taken from your table. Then the second state we gave the pressure P2 and they gave the X2, that is mixer. So we can again take these values from the pressure table. So corresponding value of 0.2 megapascal can be taken to found H2. So H2 can be calculated as HF plus X2 into HFG. So you know X value, then we can take HF and HFG value. Then if you substitute, we can calculate the H2 values. Right. So we calculated H1 and we calculated H2. Then we need to find the exit velocity. That is will be, how can we calculate? By the use of this equation. So we can substitute H1, we can substitute H2, then the unknown value V2 can be. So if applied, then you can get the exit velocity V2 as 1078 meter per second. So you can cross check values. Definitely you will get this value. So the thing is, we have to find the exit velocity. So we already found it. Right. So this is the application of a nozzle of steady flow energy equation. Likewise, we have another problem. They are at 10 degrees Celsius and 80 kilopascal enters diffuser. So you have to look. You have to use the same equation again. So the nozzle and diffuser, they have the same equation. So the known values were P1 given, P1 given, V1 given, and A1 also given. We need to find we know V2, that is the volume of 2, to be equal to 0. I think they gave that's the flow velocity differential. The velocity is very small compared to inlet velocity. So they take V2 is equal to 0. Right. So same we can calculate the other properties. So from ideal gas law, we can have PV is equal to mu RT. So here we can calculate a specific volume at state 1. Then this mass flow rate can be found from the equation m dot is equal to A into B divided by small b. So we know the value of V1 and we know the value of A1 and we found the value of V1, small v1. Then if you substitute, we can get the value of mass flow rate m dot. Then if you want to find the enthalpy, that is H1, then H1 value will be, we can directly find from the equation, that is NCP dt. NCP CP d1, H1 will be equal to Cp into T1. So this Cp value can be taken as you can check from the table. Then T1 value is given. It's 10 degrees Celsius. You have to convert in Kelvin. And if you substitute, we can get H1 value. Then if you use this energy balance equation, V2 will be 0. So we can have this as 0. So H2 can be calculated as H1 plus V2 by V1 by V2. So V1 squared by 2. So if you use this formula, again we can get the H2 value. Then again we know the H2 value, so we can use the same formula to get our on the T2 value. So H2 is equal to Cp into T2. So we can reorder this equation. Then we can Cp. Right. So we found the H2 value 304.42. Then we know Cp value 1.005. And if you calculate, you can get the temperature at state 2. Yes. The thing is, you have to use the formula, simplified energy balance equation for nozzle and diffuser. Then also there another application is turbine and compressor. Turbine and compressor. So in turbine there will be mass flow. Also we can get work output. But in compressor, just compare. You know what is turbine. So we have to give the mass flow. We can get the work as an output. Then in compressor, we need to do work on the compressor. Then we can get the mass flow. Right. There will be mass flow, and we need to give the work done into the compressor. So you know we can take the compressor in our general compressor. So we can we already discussed in our. We can have the compressor in our refrigerators. We can have this turbines in our power plants, steam power plants. So these are the applications. So turbine is a control volume. Is a steady flow compressor. So just take this schematic representation. Yes, a turbine is a device, a work producing device. through the expansion of fluid. So fluid can be expanded. So here the inlet expand. So V1 gets V1 will be less than V2. So we will expand the volume. Then we can get the work as an output. So that is the principle of turbine. Then the compressor. So the principles were already discussed in the introduction class. Just go through that. As fan, so pump will be a model of compressor and fan will be a model of compressor. Pump and fan will be a model of compressor. This you can see your any puncturing shop, the compressor. So this device is used and involves work output, work input. So we need to do as an electrical work input. Then we can get the fluid. Fluid in the sense we can use the fluid as a gas. We can use fluid also gas, liquid or gas, right? So by the mean of work we can get the can be increased. Here velocity can be, the volume can be increased. The thing is, the steady flow energy equation can be applied for this turbine and compressor. These values can be neglected. So there is no P to Q, there is no PE, there is no KE. So we can neglect. Then we can have the energy equation as yes, this one. So this is a actual energy equation. So we can this is energy equation. Then we can neglect. So there is no velocity, there is no potential energy. So we can in, there is no in and out. So there is no Q, but there is W. But there is W. Remember that. So we can have there is W, but W will be in out only. So we can neglect this W in. So M in M dot in into H in equal to W dot in plus M dot out, out W dot out plus M dot out into H dot H out. So we can avoid this mass flow rate by what, right? So we can have so this is keeping this side and this is bring this side to have this equation. So W dot out will be equal to M dot in into H in minus M dot out minus into H out. So that can be written as M dot. So we can take so there is M in will be equal to M out. So we can take mass flow rate as constant. Then we can have H2, that is H in minus H2, H1 minus H2, H in minus H out. So this is the final equation for compressor and turbine. So this is for turbine. Then for compressor, again we can there is no V2. Yes, we can avoid this, and yes, W in will be there. So we can avoid this. There is W in, there is no W out, and we can write this equation. And again we can have this in, and we can bring this M in. To RHS, then we can have W in will be equal to, so M in will be equal to M out, so we can have M dot is constant and H2 minus H2. Just remember this formulas are alone. So if you want to derive this equation, in some other cases, any questions may be asked. So just know how to derive this equation. The thing is, you can have W in for a compressor is M dot into H2 minus H1. Where in the case of a turbine, W out can be calculated by multiplication of mass, net flow rate of mass into H1 minus H2. Here H1 minus H2, here H2 minus H2. Then the use of that formula, we can calculate this. We can solve this problem. So yes, energy. W is given, the energy is given. So inlet properties, and these are the inlet property. These are the exit properties given. Then also they stated 5 megawatt power. Power is 5 megawatt used there. So what do we want to find? Then determine the work done. So we have to calculate the W here and check it turbine. So we can have corresponding pressure value of 2 megapascal in our property tables. Then also Z is there here. Z is there, V is there. So we have to use all the energy, all the terms of energy equation. So if these values were given, we have to use the whole formula. Right. So from state 1, we have P1 value, we have T1 value. So corresponding, these are same. So we have to check. Then you have to take the H1 value. Then for the corresponding state of 2, we have this value. So the condition is, if you check, the condition will be saturation mixture. So we can have the equation. Then we can found the H2 value. So we found H1 value. For this, so we can have the energy balance equation as like this. So we don't have a Q in this question problem, and also we don't have a W in. The other terms will be there. Then we need to found this H out minus H1, right? So this can be found delta H is equal to H2 minus H1. Then delta K is equal to V2 square minus V1 square by 2000 in the form of kilojoules. Also we can found the delta PE. The thing is, the energy balance equations remains W out will be equal to change in entropy, enthalpy, plus change in kinetic energy plus change in potential energy. So what we already found. So we can substitute to get the work output. We can get work output as 872.48 kilojoule per kg. Then we need to find the mass flow rate. So mass flow rate equation will be m dot yes, out is equal to, sorry, W is equal to, small w is equal to capital W by M. So this also can be written as M is equal to, yes, capital W by small w. Right. This capital W, that is our power, work. they given, so 5 megawatts is taken here. Then if you yes, if you divide that by W out, this is actual again divided by output out, you can get the mass flow rate m dot, that is 5.73 kg per second. The thing is, just you have to remember the steady state energy equation for turbine and the compressor, the turbine and condition of compressor. Then the next problem will be based on our this compressor. They gave so this is for compressor, right? So we know for compressor W in will be there. Right. This is compressor. W formula will be simplified energy balance formula will be W dot in will be equal to m dot into H2 minus H1. Here temperature will be given, so we have to take this. We have to account this Q dot also. Then we can have the other properties. So we know these properties. T1 is given. T1 is given. As usual, we can found the H1 value. Then at state 2, they gave P2 value and T2 value. We can take H2 value. So we can have H2 value and H1 value. Then yes. So if you substitute, I think mass flow rate M is given. The flow rate. Mass flow rate is 0.02, so we can directly substitute, and I think Q is the given. Yes, heat loss of 16 kilojoule per kg. So they gave a Q also. Heat loss minus of Q out, right? So 16, we can directly take 16 in the formula. So if we substitute, we can get work input. So we have to give 2.74 kilopascal kilowatt work into the system, into the compressor. Then we have 2-3 slides only, so just have 5 minutes. Will complete. So another application of steady state energy equation is throttling valve. So just this is a adjustable throttling valve is this types. There is adjustable porous plug. There is a capillary tube. So we discussed what is capillary tube and what for it was used in our engineering applications. Then flow. So this throttling valve is a flow restricting device that causes a significant pressure drop in the fluid. So we can reduce pressure. Some familiar examples are ordinary adjustable valves and capillary tubes. Yes, these are the examples of our throttling valve. So this capillary tube will be a type of throttling valve. Then the application of this is same, but here only we have pressure. Right, we can get reduced pressure. So here P1 value is given, sorry, yes, 1600 kilopascal and 1500. So there is no value for 1600 kilopascal in their property table. So if in our table the for corresponding value of 1600 kilopascal is available, we can take directly, or else you have to interpolate. So this is interpolation. So check if there is a value for 1600 in our property table. If there is no, we have to interpolate. Then we can take these values. So if you compare this P1 and T1, we can get the H1 value and P2 value. Here H1, if you compare, if you interpolate, H1 will be equal to H2. Then we can have these values. So T2 values can be taken, then all the other values can be derived. And yes, ma'am.
சார்
Yeah.
இந்த சர்வே முடிச்சுக்கலாம் சார்.
அவ்வளவுதான் முடிஞ்சுடா.
ஓகே சார்.
சொன்னேன் 3 ஃபைல்ஸ் இருக்குது. அதோட முடிஞ்சு.
ஓகே
Right.
சார்.
So the thing is again the same. So we have to head. So we have state and value. So the unknown value action will be found, and this comparison, the action will be equal to H2 here. Then you can take other properties from the interpolation. Then so T2 will be equal to T saturation. You can check the T2. So that will be equal to 201.3. So the same for the same state 2, x2 value is calculated. So from this equation, so we have HF and HG. So we need x here. So another we can calculate this. Then we can use this x to calculate V, specific volume at T2. So it's a thing we need to calculate. So we can calculate the V, throttling one, right? Again, final application is mixing chamber. So it's like our normal hot and cold water mixing in our tap section where the mixing process takes place. An ordinary T elbow or a Y elbow in a shower, for example, serves as the mixing chamber for the cold and hot water steam. So this is the example of mixing chamber. So this is also application of a steady flow energy equation. So this mixing chamber will be look like this. And this mixing chamber energy balance will be again. So we can neglect what are the terms. There is no the terms. Then we can neglect. Then we can have the final equation as m1 dot equal to m3 dot h3 minus h2 divided by h1 minus h2. So what is mixing chamber? We can have the mixing chamber of a schematic representation. Where is that? Yes, this is the mixing chamber. So we can add 2 inlets and we can expect 1 output. So this is the mixing chamber. So there is H1, there is H2, there is H3. Right? There is P1, 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 H1. There is P2, V2, H2. Then we can expect P1 as a mixer. So just of that, we can have this equation. Let's go through this. Then also we have heat exchanger. So the fluid flow will be there. So we will pass some cold fluid in this. And we will pass some hot fluid in this. So there will be heat exchange between these two fluids. So heat exchanger is a device where 2 moving fluid streams exchange heat without mixing. So there is no mixing of these 2 streams. So heat exchangers typically involve no work interaction. There is no work interaction, negligibly kinetic and potential energy changes for each fluid stream. There is no W, there is no PE, there is no KE. If you apply this same for this to solve this problem, again same, right? So just have this equation, simplified energy balance equation for the case heat exchanger. There will be m dot into Cp into, there is S in the sense supply. Right, so just go through this problem. Then the known values can be taken to found the unknowns values. Then P1 from P1 we can found H1 W is water. So we have two fluids, right? So we have two fluids. So S is sodium, liquid sodium, and W is water. So from that we can have H1W, and we can have H2W. Then so from this equation, so I think these values were given. Yes, this H1W we need, H2W we need, then T1S and T2S will be there. So we can substitute, and also we can take CT value of sodium from your table. Then we can get the mass flow rate of water, finally 4.62. Then we can have the heat flow rate, heat transfer rate, that is heat transfer rate of W will be is equal to mass flow rate of W into H2 minus H1. So we can have these values. So M2 will be the M dot will be there. The M dot we found out here. Then we know H2W, we know H1W. Then finally we can get the Q dot W. The process is same, but only the thing is formula will be differ and the condition. So based on the condition, we can derive the formula. The thing is only we have steady flow energy equation with the Q, W, mass flow rate, kinetic energy, and potential energy. So depending on our applications, we need to reorder, or we need to simplify the energy balance equation. Then we can apply the equation for solving the problems. Right. So these are the applications of steady flow energy equation. That is the application of first law of thermodynamics. Then in the next class we can have the second law of thermodynamics. We can have the second law of thermodynamics and then only you can get understand. Just try to solve the assignment by your own. Don't copy. Just try to cooperate. And that's it. So sorry for the delay. And so if you have any queries, you can wait and ask, or else you can hang up. Thank you. Have a good day.
Thank you.